So let's start off with a super simple one, such as the limit as x goes to 3 of this equator right here. So first thing I do is I try the plug-in method. I try to see if I can just evaluate the function. Is I plug in 3, that gives me 9 plus 9 over 3 plus 3, which gives me approximately 18 over 3. I don't see an issue with this. Looks like a nice function, continuous, everything's good. We're done. Sometimes you don't even need limits. Why? Because the function is continuous at that point. Okay? See, we could have done without the limits. We could have just evaluated the function, and the value of the function is the same as the limit. Of course, that occurs when the function is continuous. Try it again. Let's try the plug-in method. So you try your luck here. I'm plugging in x goes towards infinity, 7 over a huge number. Well, that's going to end up in the 0 bucket. There's no controversy here. No matter which large item you pick from the infinity bucket, 7 divided by that large item will be in the 0 bucket. It'll be incredibly small. Let's try that again. What about this? 7 raised to the 1 divided by infinity. Well, there's no controversy here. 1 divided by infinity would be 0, and that would leave you to believe that this guy is equal to 1. Of course it is. There's no problem. A lot of times, the function, if the function is continuous, not a lot of times, every single time that the function is continuous, the plug-in method will work and you'll be done. There's not even any need for limits. You just plug it in and you're done. Then what happens here? Sometimes you try to plug it in, and what happens? If you try the plug-in method here, you get 0, 0. Now you see, whoa, what happened here? 0, 0, that's an indeterminate form. You have to say it depends how little the 0 is on the numerator and how little the 0 is on the denominator. Not all zeros are created equal. And so not all zeros in the bucket are the same. They're all really close to 0, but they may not be equal. So we need to find out this ratio. The perfect cure for that, of course, the limit. And here we review our limit techniques using the rewrite method. By rewrite, I just mean use your algebra skills to try to see if you can write this function into a different one that matches that one at almost every value, such as this one. You could say x squared. Well, how about this? I wonder if I have that already here. Yeah, so you could take that and factor it, such as that, and then we can cross out one of these. That goes and that goes, and that leaves you with a different point of view on the limit as x goes to 3. X plus 3. Now you try your luck again with the plug-in method. Of course, that's going to give you 3 plus 3, which is nice. So this idea that sometimes you can algebraically manipulate the expression and do some simplification, as long as you don't change it too drastically. This just changes the function at one point, so it's not going to hurt the limit. As long as you don't change it too drastically, you can give yourself a chance at the plug-in method again. That works nicely there. The rewrite method is nice. Of course, it has its drawbacks. Sometimes it's not that easy to do the rewrite here. Often it's incredibly difficult, and so it's nice when it works. It's not a cure-all method. Let's try some other techniques. Limits to cure indeterminate form. So here, if you try the plug-in method, you get, of course, 0, 0, which is a famous indeterminate form, and you say, well, it depends on how large that 0 is and how small each one of them is. And so the plug-in method is not going to work. This revealed to us that we have an indeterminate form, so you've got to do some other work. Another type of work that you can do would be to try to see if you can graph the function. That would mean simply plotting points here. I could plot in points, and you can plot in points really close to 0, because x is going towards 0. X is going towards 0 from both sides, and try to observe what the y is doing. The y is going here. I'll save us some work, but if you could just make a little chart here, x's and y's, and x is going towards 0 from both sides, negative 0.001, negative 0.00001, etc., 0.001, 0.00001, etc., and you get numbers here that are really close to 1. Just making things up. No, not 0. There it's undefined. This we also call the engineer's method, by the way. We just try to guess what the number is based on a little chart of values. 0.999, 0.99. You could put them in a calculator and see for yourself. So one way is if you can look at the graph or if you can get some sort of idea of the graph, depending on how trustable your idea is, that might get you to the right limit. In this case, it's approaching 1. It looks like the numbers approach 1 from both sides. And so in this case, the ratio of this type of 0 compared to that 0 was equal to 1 in this particular case. Okay? That's called the graphing method. If you can take a look at the graph, you may be able to just pinpoint or guess what the limit is. Okay? Another tick. So we have the plug-in method when it's continuous. We have the rewrite method when you can tweak it algebraically. We have the graphing method. And of course we have the engineer method, which I just alluded to. Alright, let's have a look at this fourth method I alluded to earlier. Engineer's method. It's just a guess to try to figure out what the limit is. As an example, let's take a super famous one like this one. The first thing you might be tempted to try the plug-in method and say, hey, maybe that function is continuous. Maybe I could just go like this, 1 over infinity raised to the infinity. And you try and see what that is. That looks like 1 plus 0 raised to the infinity, and that looks like 1 to the infinity. And you say, whoa, that's one of the indeterminate forms. It depends on which item from the one bucket I choose. If I go to the right, it'll go to infinity. If I go to the left, it'll go to 0. What if I go a little tiny bit to the right? Like this is 1 plus something little tiny small. All bets are off. So for sure this is indeterminate form. We have to do more work. So as the title suggests here, we're trying a new technique called engineer's method, which at the end of the day it's just a guess. That's what engineers do. They don't prove anything. They just try to guess based on some numerical evidence. Don't be mad, I'm just joking. Alright, so you could try the engineer's method on this. You just go like this. If x is going towards infinity, what is my y going towards? So you try some y's that are x's that are going towards infinity. Perhaps 1,000, perhaps 10,000, however much your calculator can handle. Your calculator is that soulless piece of plastic. Let's see, some of your calculators can't handle that, but I suspect that most of you will, with one calculator or another, get to this conclusion. This is roughly about 2.7, 2.718, 2.71828. And of course, if your best guess would be as x goes towards infinity, your y's go towards e. Super famous limit e. Not a proof, but a good way to access a lot of these limits. Get your hands dirty, try to plug in some numbers in there and try to make a best guess of what the limit is. That's the engineer's method, fourth method. That gives us 4 techniques for limits. Real quickly, let's review them. The plug-in method works great when the function is continuous. Done. How do you know if it's not continuous? Well, you'll get one of the famous indeterminate forms 9 out of 10 times. You'll get one of the famous indeterminate forms. In that case, if not, then you got to try some of these other things like engineer's method, graphing method if you can graph it, or rewrite method if you can use your mad algebra skills to remove the removable discontinuity. You may have a shot at the rewrite method. Sometimes the algebra is a little crazy, but you should always attempt. And that gives you 4 methods: plug-in method, engineer's method, graphing method, rewrite method. Okay, there it is. That's your short little review of limits. Peace. We'll see you guys here next time.